This is part 2 of the walkthrough of the AQA GCSE Chemistry 2023 Higher Tier Paper 1. Question 6. This question is about uses of metals in electrical wires. Electrical wires can be made from aluminium, copper, silver. Figure 6 shows 3 uses of electrical wires. Table 5 shows information about the metals. The higher the value for electrical conductivity, the better the metal is at conducting electricity. So our 3 metals per kilogram in pounds. 6.1. Evaluate the use of aluminium, copper and silver for the types of electrical wires shown in figure 6. Use table 5, 4 marks. So we have to evaluate, which means that we need to think about advantages or pros. We need to think about disadvantages, cons. We need to compare, and then we need to give our conclusion or judgment at the end. So we need to think for these 3 properties in the table, which is going to make it suitable for each metal to be used for each of these 3 functions. So what we should do first is look at our table and then start to do our comparison, because once we do the comparison, then it will help us with our advantages and disadvantages. So let's start with electrical conductivity. Remember that it says the better the metal is that conducts electricity when the value for electrical conductivity is higher. So looking at the table, we can see that silver has got the highest electrical conductivity. Aluminium has the lowest. So that means that silver will conduct electricity well. Aluminium won't do that as well. Our density. So think about mass in a certain volume. And density is linked to how heavy the metal is. So again, silver, highest density, aluminium, lowest density. And then the cost of metal per kilogram in pounds. Again, silver is highest, so most expensive. Aluminium, least expensive. Okay, so we've done our comparison here. We've just got to think now about those different devices or functions of those metals. So let's go back up to the figure. So first one is overhead power cables. Well, for our overhead power cable, let's think about what we would want it to have. We definitely want it to have a high electrical conductivity, because the whole point of having these overhead power cables is that electricity is getting to people's homes. So we want high electrical conductivity for that. Well, it needs to be set up, built, because it's part of the national grid. So that means that we want the cables to be high, above ground. That means that the density needs to be low. So we want low density for these power cables. Imagine if that the density was high for them and then they fell, it would cause a big problem. It'd be quite dangerous. So we want density to be low for that. And then for our cost, we want it to be fairly cheap, because we know that this is going to be over many places in the UK. So we want it to be relatively cheap. Let's think about our wiring in homes now. Again, we want high electrical conductivity for that. The density, again, we want it to be fairly low. But the density doesn't need to be as low as the overhead power cables. So if we can find something that's medium density, that'll probably be okay. And in terms of the price, we definitely need this to be cheap, because this is going to be in people's homes and it needs to be affordable for them to buy it. And lastly, printed circuit boards. So that's probably going to be in certain devices like remote controls, phones, etc. Again, you want the electrical conductivity to be high. Density, well, we definitely want the density here to be low, because it's going to be in smaller devices. So if it's going to be in small devices, we don't want the device to be too heavy. And then lastly, the price. Well, of course we always want things to be cheap. However, it's going to be bought by people for specific reasons. So we can write cheap, but it doesn't have to be as cheap as overhead power cables and wiring in homes. Something not as cheap as others. Okay, so it looks pretty similar in terms of identifying the functions of each of these and what properties we like. But now we've got to really do our comparison now. So in terms of high electrical conductivity, we definitely want overhead power cables to have the highest high electrical conductivity. In terms of density, we definitely want the overhead power cables to have the lowest density also. In terms of the price, we want the wiring homes to be cheap because we want it to be affordable. So let's look at our table now and see if we can match our metals to what we want for our devices. So again, electrical conductivity. Highest was silver. So we could say silver would be useful for all of them. However, let's check our density. The problem is that with silver, it's got the highest density. So silver's not going to be good for our overhead power cables. Which one has got a high electrical conductivity but lowest density? Well, that's going to be aluminium. And if you look at the price for aluminium, it's going to be the lowest also. So I think the most suitable for our overhead power cables would be aluminium, then copper, and then silver, in that order. Let's do the wiring homes now. Again, we want high electrical conductivity. Silver can provide that. But remember, it's got the highest density, so it's not going to be useful there. Remember, we don't need the density to be the lowest for our wiring homes, but we definitely want it to be the cheapest. So silver is not going to be suitable for that. So the best one for our wiring home then would be copper. So for wiring homes, the order would be copper, then aluminium, and then silver. And then lastly, for our printed circuit board, again we want high electrical conductivity. Silver can provide that. We want a low density because we're going to be moving the devices. So silver is not going to provide that. And we want it to be cheap, but not as cheap as the others. And silver is the most expensive. So our order that would be most suitable for our printed circuit boards, in this case then, low density, but not as cheap as the others, be aluminium, then copper, and then silver. So let's just check one more time before we can formulate our answer. Aluminium used for overhead power cables, copper used for wiring in homes, and aluminium for printed circuit boards. So let's formulate our answer now. So we're going to start with our comparisons. So our comparisons was thinking about which one had the highest electrical conductivity. And we saw that silver had that. The density, we saw that aluminium is the lowest density. And our cost, aluminium was the cheapest. So what are we going to say now? So we're going to say then that for our overhead power cables, the best choice would be aluminium. Then our reason for that is going to be due to the density being the lowest and is cheaper than copper, despite having a lower electrical conductivity. Then we can discuss the wiring. And we said that copper was the best for that. And our reason again, it's got a higher electrical conductivity than aluminium, but even though it's got a higher density, the price makes it affordable. And then lastly, we just make a few quick points about circuit boards. Okay, so we've made our judgments for all three. We've compared, and then we've given our pros and cons. Six 6.2. Describe how metals conduct electricity. So this is a very common question that you'll find in chemistry papers. So remember that metals conducting electricity is due to there being metallic bonding. And if we do a basic structure of metallic bonding, you've got positive metal atoms in the structure. And they're surrounded by a sea of delocalized electrons that is then able to carry the charge throughout the whole structure. So just describing that in words should get us our marks. Six 6.3. Electrical wires are usually made of pure metals and not alloys. This is because pure metals are better electrical conductors. Suggest why alloys do not conduct electricity as well as pure metals. Answer in terms of structure and bonding. So, it's not alloys. So we've got to remind ourselves, what is an alloy? Well, an alloy is a mixture of metals simply. But why would they not conduct electricity as well? Well, thinking about our previous answer now, we said that the reason why they're able to conduct electricity is really because of these delocalized electrons are going to carry the charge through the whole structure. But what would be different in terms of our structure in an alloy? Well, we'll still have some metals and they're going to be positively charged. But the problem now is you're going to have different size of these metal atoms. And because there are different sizes now, it's not going to be a regular, even structure like what was drawn here. So the problem with that now is that you don't have these lovely layers like you'd have in your pure metal. And that also means that there'll be more of a challenge for the delocalized electrons to move. and that means then the charge can't be carried through the structure. Question 7. This question is about electrolysis. Aluminium is manufactured by electrolyzing a molten mixture of aluminium oxide and cryolite. 7.1. Complete the half equation for the reaction occurring at the negative electrode. Well, what's going to happen at a negative electrode in electrolysis? We would expect a positive ion to be attracted to it, and that positive ion would gain electrons, thereby becoming reduced. So in this question now, you can see our equation. We've got aluminium, which is that positive ion. It's supposed to be picking up electrons, and then we're going to form aluminium metal. But balancing it now, aluminium here has got a charge of 3+, so it's lost 3 electrons at this point. What we're trying to get to is aluminium, where it has its normal number of electrons. So to balance it, we just need to put a 3 in front of the electron symbol, and that means that 3 electrons would get picked up by aluminium ion. 7.2. Cryolite contains sodium ions as well as aluminium ions. Suggest one reason why sodium is not a product of the electrolysis. Right. Well, we've got 2 positive ions here. Why is sodium not going to be the product but aluminium is? Well, the thing about electrolysis is it's also to do with reactivity. In this case, we're dealing with metals, so we have to use our reactivity series. So please stop calling me a careless zebra. Instead, try learning how copper saves gold. So our sodium is here, group 1. Our aluminium is here, group 3. So in terms of electrolysis, the less reactive metal is what gets displaced, and that's what gets produced at the electrodes. So in this case, sodium is more reactive than aluminium because it's higher up in the reactivity series. So that's the reason why aluminium gets produced and not sodium. A student investigated the electrolysis of an aqueous solution of a different compound. Figure 7 shows the apparatus. So we've got our test tubes, which are covering our electrodes, which are inverted inside an aqueous solution. 2 stoppers are there, and the electrodes are connected to a power supply, which is standard electrolysis, especially which you do in schools. Hydrogen was produced at the negative electrode, and oxygen was produced at the positive electrode. Explain that oxygen was produced from water during the electrolysis of this aqueous solution. So hydrogen at the negative electrode. So as I was saying before, if something's going to go to the negative electrode, it's got to be a positive ion. So in this case, hydrogen would have to have started as a positive ion. Oxygen was produced at the positive electrode. So oxygen, just do the opposite. It's attracted to the positive electrode, which means it had to be a negative ion. Now oxygen is in group 6, the periodic table, so it wants to gain 2 electrons to have a full outer shell, so it would be the oxide ion, which is O2-. So how is the oxygen produced from water? Because yes, it was an aqueous solution. Well, as you looked at in part 1, water consists of H plus and OH minus ions. So what would happen to the water is the water is split into these 2 ions. That should be our first point there because it's telling us how we're producing the 2 ions. Now we're focusing on the oxygen from now. So we've got to describe what's happening there. Well, we've got OH minus, so we don't actually have oxide on its own. But we do know that the oxygen is going to be produced at the positive electrode. So if it's produced at the positive electrode, it's going to lose electrons. Now, if it's attracted to the positive electrode and electrons are lost, using our oil rig, oxidation is loss of electrons. So oxidation will occur at this positive electrode. So the OH minus ions are oxidized, and that's what produces the oxygen gas. So water splitting, probably be our first mark. Mentioning the ions that we produce, be our second mark. And then the attraction to the positive electrode, and then the oxidation will give us our 4 marks here. 7.4. The student compared the volumes of the 2 gases collected. How can the student change the apparatus in figure 7 to compare the volumes of the 2 gases more accurately? Give one reason for your answer. So you need to change the apparatus in figure 7. So let's go back to figure 7. They want to measure the volumes more accurately. So a change to this setup to measure volume. Well, if we want to measure volume, we need pieces of equipment to measure it more accurately. Of course, what would normally happen was we could just look at the 2 test tubes and then decide which one has got more gas in there, because we expect less water or less solution to be in there, and then that would mean it has a greater volume of gas. But if we want to measure it more accurately, we have to think about a piece of apparatus that we can use to measure volume. We can use beakers. Putting 2 beakers in a beaker is going to be quite difficult. So we could easily use a measuring cylinder. And why is a measuring cylinder going to be more accurate than using test tubes? Well, what does the measuring cylinder have on it? It's got scales, intervals. And of course, you can just measure the actual volume by just reading the scale itself. So our change would be replace test tubes with measuring cylinders. And then our reason is measuring cylinders have a scale. 7.5. The overall equation for the reaction is shown. What is the volume of oxygen produced when 20 centimeter cubed of hydrogen has been produced? Tick one box. So we want to find out the volume of oxygen when 20 centimeter cubed of hydrogen has been produced. Well, we have our equation. 2 moles of water give us 2 moles of hydrogen, and because there's no number in front of our oxygen, that means you have 1 mole of oxygen. So for every 2 moles of hydrogen, we get 1 mole of oxygen. So if we've got 20 centimeter cubed of hydrogen, we should expect half of that for oxygen. And half of that, 20, is 10 centimeter cubed. Question 8. This question is about elements in the periodic table. Argon has the atomic number 18. Explain why argon does not form compounds. Answer in terms of electrons. So argon has the atomic number 18. If we convert this to our electronic structure now, our electronic configuration now, that would be 2 in the first shell, 8 in the second shell, and that would mean 8 in its third shell, which is the outer shell. And that's the reason why argon is in group 0, which is the noble gases. What's special about noble gases with having 8 electrons in their outer shell? They don't need any more, they don't want to lose any. So they're stable and are going to be unreactive. So in terms of electrons, we've already explained the reason. They have a full outer shell of electrons, so they don't need to gain or lose any. (8.2) Phosphorus is the element below nitrogen in the periodic table. Predict the formula of the compound formed between phosphorus and hydrogen. So we've got phosphorus, which, if we think about our periodic table now, is a non-metal. We have hydrogen, which we definitely know is also a non-metal. So we know that if there are two non-metals, there will be covalent bonding here. And covalent bonding is sharing of electrons, as we saw in part 1. Now, hydrogen only has 1 electron, so it needs 2 electrons to have a full outer shell. Phosphorus is below nitrogen, and nitrogen is in group 5. So that means in its outer shell it has 5 electrons. So how many does it need to gain a full outer shell? It needs 3 more electrons to gain a full outer shell. So where would it get those 3 electrons from? It would have to get them from hydrogen. But it can't just get them from 1 hydrogen atom, it would need to get them from 3 hydrogen atoms. Now if phosphorus and nitrogen are in the same group, that means they're most likely going to react the same. So if nitrogen reacts with hydrogen, we know a common compound that it forms is NH3, which is called ammonia. So a similar reaction, just replacing the nitrogen with phosphorus, would be PH3. And that would be the formula. (8.3) Tellurium is the element with the atomic number 52. Predict whether tellurium reacts with metals. Explain your answer. Answer in terms of the position of tellurium in the periodic table. So let's find tellurium in the periodic table. Tellurium is in group 7. So group 7 are halogens. And we know that these are non-metals. So think about the other group 7 elements that we know: chlorine, fluorine, bromine, iodine. We know that these are non-metals. So they would form compounds with metals. So they would react with them. So if it's in group 7 and it's got similar properties, we could confidently say that tellurium would react with metals. However, what we must also remember is that as we move to the right-hand side of the periodic table, there are still some metals that are there. And the metals that are on the right-hand side of the periodic table are going to be at the bottom of that right-hand side. So you might have seen like a staircase that's shown on the right-hand side of some periodic tables to indicate to you where the cutoff point between the metals and the non-metals are. Tellurium would actually be below that cutoff point, so we could actually say that no, it would be a metal because metals don't usually react with other metals. So depending on your answer and your explanation, you could either say yes or say no. Barium is an element in group 2 of the periodic table. Barium reacts with hydrochloric acid. 8.4. Suggest 2 observations that can be made when barium reacts with hydrochloric acid. Well, what we can do is we can do an equation to help us with this. We know that a metal is supposed to react with an acid in this case. We're going to form a salt and hydrogen. This is the general rule whenever we have a metal with an acid. So what would we expect to see? You place a metal in an acid, you're going to see fizzing. So fizzing is definitely one observation that we would see. But will the metal always remain there? Will we always see it? No. The metal will essentially dissolve and then help to form the salt. So in this case then, the metal being barium, barium would eventually disappear. (8.5) Write a balanced symbol equation for the reaction between barium and hydrochloric acid. Well, by us doing our general equation, we've reminded ourselves how to do this. So we know that barium is Ba. It's going to react with hydrochloric acid, which is HCl. We're going to make a salt. And remember that salts involve the metal first, so Ba would be first. And then the unique part of the acid, which is Cl. And then we're going to form hydrogen, which is a diatomic molecule, and that's H2. However, they've told us that barium is in group 2 of the periodic table. So if barium is in group 2 of the periodic table, when it reacts with this chlorine, it's going to form an ionic compound, because barium is a metal, chlorine is a non-metal. So barium would form a positive ion, and I would have a charge of 2+. Chlorine is in group 7 and only wants to gain 1 electron, so it would have a charge of 1-. But barium needs to donate that other electron to something else, so it would donate it to another chlorine atom, so that would mean that the formula for barium chloride would be BaCl2. Now we need to balance the equation as they've told us. So let's just check now by doing our normal balancing method. We write the elements underneath, and then we find out how many atoms do we have on each side. So barium we have 1, hydrogen on the left you have 1, chlorine on the left you have 1. Barium we have 1, hydrogen we have 2, and chlorine we have 2. So for us to balance this, barium atoms are fine. We just need to increase our number of hydrogen and chlorine on our reactant side. Remember, our smallest number that we can put is a 2. So by putting a 2 in front of hydrochloric acid, it will change our atoms of hydrogen and chlorine to 2, and it's balanced. Question 9. This question is about displacement reactions. Iron is extracted from iron oxide by a displacement reaction with carbon. The equation for the reaction is shown. 9.1. Which substance in the equation is reduced? Give one reason for your answer. Answer in terms of oxygen. So what substance is going to be reduced? Now we just reminded ourselves about the oil rig mnemonic. So reduction is gain of electrons. So from our equation, we need to identify what is going to gain electrons. Well, let's start at the left here. We have iron oxide. Well, it's an ionic compound once again. Oxygen in group 6, so it would have a charge of -2. But there are 3 oxygen atoms. So the total negative charge would be -2 times 3, which would be -6. We only have 2 iron atoms. So we need to think about what would be the charge on them for us to get a +6 to balance out this compound. So we take that -6, divide it by 2, so then we'd actually have each of the atoms of iron having a +3 charge. Carbon is on its own, has no charge. Iron on its own, no charge. So if we stop at this point right now, we can see that our iron has actually changed from +3 to 0. So remember that metals always form positive ions. So what's happened is this iron has gained 3 electrons to form this iron metal. But what we've been doing is we've been explaining it in terms of electrons. We need to answer in terms of oxygen. Now, using oil rig won't help us because that's oxidation is loss of electrons, reduction is gain of electrons. What's our other definition of oxidation? Oxidation is gaining of oxygen. So reduction would be loss of oxygen. So what's losing oxygen in this equation is definitely the iron oxide. So our reason is it loses oxygen. So the substance, really the compound, is iron oxide. It says answer in terms of oxygen, so it's iron oxide. 9.2. Which expression shows how to calculate the mass of carbon needed to produce 1 mole of iron from iron oxide? The relative atomic mass of carbon is 12. Tick one box. Right, so this question is actually about reacting masses, but we're just doing the expression. So for reacting masses, we need to identify which, from our equation, which substances are we dealing with. So we're dealing with carbon and iron. So we're thinking about our 2 here. So what do we need to think about when doing normal reacting masses questions? We need to think about the mass. We need to think about the molar mass, which is the relative atomic mass or relative formula mass. And then we need to find the moles from there. Now in this question we are not giving the mass. We're not given the mass. But we are given a number of moles. So 1 mole of iron from iron oxide. So if we were to continue, we would need to find the relative atomic masses. Well, we're given the relative atomic mass of carbon. We know that it's 12. But then we would need to find a molar ratio. So the molar ratio is the next thing that we would need to find out in the steps for reacting masses. Now, to find the molar ratio, we should be looking at our equation and what numbers are in front of our interested substances. So in front of carbon we see a 3, in front of iron we see a 2. So that means for every 3 moles of carbon we have 2 moles of iron. For every 2 moles of iron we have 3 moles of carbon. So the molar ratio is 3 to 2 in this case. Now remember what we're trying to find here. We're trying to find the mass of carbon. So to find the mass of carbon ultimately, we would need to use our equation, which is mass equals moles times RAM. Now, it says that we've got 1 mole of iron from iron oxide. Remember, we actually have 2 moles of iron from the equation. So for us to find out the number of moles of carbon, it would actually be 3 over 2. And then, once we found that out, remember we need to multiply that by our relative atomic mass. So our relative atomic mass would be 12. We're trying to find the mass of carbon. So we're looking for an expression of 3 over 2 multiplied by 12. And that's the second box. A student investigated displacement reactions of 4 different metals represented by A, B, C, and D. A, B, C, and D are not the actual chemical symbols for the metals. The student added each metal to aqueous solutions of the metal nitrates, observed whether a reaction took place. Table 6 shows information about 3 of the reaction mixtures. Okay, so we have the 3 metals, we have 3 metal nitrate solutions, and then we have an equation. Straight away we can see that one of them has no reaction. 9.3. The ionic equation for reaction 1 is shown. Why is this a redox reaction? Tick one box. Well, redox is a combination of reduction and oxidation. And we've been dealing with the reduction and oxidation in our previous questions so far. So we know that reduction is gain of electrons, but it's also the loss of oxygen. You know, the oxidation is the loss of electrons, but the gain of oxygen. So let's look at our options. We can see that from our options, it's mentioning electrons. So we need to think then of oil rig definitely. So we're expecting then in a redox reaction, both of reduction and oxidation occurring in the same equation. So we would expect something to get reduced and something to get oxidized. So A and B. Let's look at A. It starts off on its own. So as we were doing before, it has a charge of 0. In the products, it's got a charge of 2+. So what has happened is it has lost electrons. So A has been oxidized. So for it to be a redox reaction, that must mean that B has gained electrons, so it's become reduced. And we can see that happening as in the reactant side, B has +1 charge, but in our product side, it has a charge of 0. So it's gained the electrons. So which box is showing that A is going through oxidation, losing electrons, and B is gaining electrons? Is our second box. (9.4). Which of the following metals has the greatest tendency to form positive ions? Use table 6, tick one box. So which one is most likely to form positive ions? Which one wants to do that? So going back to our table now, we want to see which one is going to form those positive ions the best. So let's look at A first. Let's go in alphabetical order. A. If we look at reaction 1, we can see A is reacting with B. Now, the one that's going to have the greatest tendency is the one that's going to be part of the nitrate compound. So what we're looking for then is which of the 4 metals wants to stay with the nitrate ion the most. So looking at reaction 1, we've got A reacting with B as part of the nitrate. What's happened? Well, A has displaced B with a nitrate. So in a reaction between A and B, A has a greater tendency. Let's look at reaction 2. C. C is on its own. It's reacting with A, which is part of the nitrate now. What's happened? C has displaced A. So C is with the nitrate now. So C is more likely than A to form the metal ions that are positive. We just seen with B in reaction 1 that it was displaced by A. So there's no other reaction here that involves B. So we know that A is definitely more likely to form positive ions than B. But then C is here again in reaction 3. So what is it reacting with this time? It's reacting with the metal nitrate, which is D. But there's no reaction. So this is displacement, of course, but there is no displacement in this reaction. So what does that tell us? That tells us that D is more reactive than C, so wants to keep forming these positive ions more than C. So we know that B is last from what we have seen here. But after B, it should have A, because A, when it reacted with C, it was displaced. But then we have C with D, and we know that there's no reaction. So after A, the most reactive would then be C, and then from what we've seen, it would then be D. So our greatest tendency to form positive ions would be from D. 9.5. The nitrate ion has the formula NO3-. Which of the 4 metals could be aluminium? Explain your answer. Use table 6. So, aluminium. What do we know about aluminium? It's in group 3 of the periodic table. So what does it mean? It means that it wants to form metal ions with a +3 charge. Nitrate ion is giving us the formula. It's 1-. So what we're looking for then is we're looking for nitrate ions, but actually 3 of them. So we're looking for this expression in our equations. Whenever the metal, whether A, B, C, or D, forms a compound with this expression here, that will be the group 3 metal, so would be aluminium potentially. So we're looking for that expression now in the table. So let's look at A. Looking at A, we see a product here, but that's NO3, got 2 lots of it. So A can't be aluminium. Let's look in our second reaction. Still seeing 2 there, so we're not happy. But we do see NO3 with 3 of them, and that's with metal C. So metal C is our option for what's likely to be aluminium. Our explanation, as we were describing then, was aluminium forms metals ions 3+ charge. But what does that mean in terms of the nitrate then? So that means for every aluminium ion, we need 3 nitrate ions. 9.6. Metal X is extracted from an oxide of metal X by reaction with hydrogen. The equation for the reaction is shown. The percentage atom economy for obtaining metal X by this method is 77.3%. Calculate the relative atomic mass of metal X. The relative atomic masses of hydrogen and oxygen are provided. So, percentage atom economy is what we're thinking about here. There is an equation that we have to recall for that, and that is the RAM, which is the relative atomic mass of the desired product, divided by relative formula mass of all reactants, and then we multiply that by 100. So what we just want to do then is we want to try and see from our information that's in the question, what do we have that we could put in this equation? Well, first of all, we're given the percentage atom economy. We know that's 77.3%. Our relative atomic mass of our desired product. Well, reading the equation, reading the information again, metal X is extracted. The percentage atom economy of obtaining metal X. So metal X is our desired product. So what we want is X. But we don't know the relative atomic mass. We're trying to find it. The RFM of all reactants now. Well, let's look at our reactants. We've got XO3 there. Remember, we don't know what the relative atomic mass is of X, but we do know it of oxygen. So we know that one atom of oxygen has a relative atomic mass of 16, but there are 3 lots of it. So 16 times 3 is 48. We need to add that to our hydrogen now. Well, we know there are 2 hydrogen atoms in every molecule, so that will be 2. But there are 3 lots of them, so that will be 3 times 2, which is 6. So it's actually going to be our X divided by 54, because that's 48 plus 6. But we still need to add that to X, because we don't know what X is as yet, and it's still part of our reactants. And then we're going to multiply that all by 100. So it's just now. So now we need to just do a little bit of algebra as we're trying to obtain a value for X. So we need to isolate X, and then we're able to work it out. So we're going to take our 77.3, and we're going to move this denominator onto the other side. So it's going to be 77.3 multiplied by 54 plus X equals X times 100, which is same as 100X. So if we just expand this now, we'll have 77.3 multiplied by 54, and then that will be equal to 4174.2 plus 77.3 multiplied by x. And that would still again be equal to 100x. Now, you still got a problem here because you have x on both sides. So you just want to get x on one side. So what we're going to do is we're going to take 77.3x away from 100x. So we'll just be left with x on the right hand side. So 100 minus 77.3 will be 22.7. So 22.7 times x will give us 4,174.2. So much easier now. We just divide both sides by 22.7 and then we'll be left with our answer. So we just need to, in our calculator, do 4,174.2 divided by 22.7 and we're left with 183.885, which you can just round to 184. So our relative atomic mass of x is 184. Question 10. This question is about titanium dioxide. 10.1. Self-cleaning windows are coated with a layer of nanoparticles of titanium dioxide. Titanium dioxide helps sunlight break down dirt particles, attracts water so dirt is washed away by rain. Nanoparticles of titanium dioxide are used instead of fine particles of titanium dioxide for coating self-cleaning windows. Suggest 2 reasons why. So, we're thinking about why nanoparticles, which you can represent by this small dot here, are used instead of fine particles, represented by this other dot here. So, we obviously know that nanoparticles are smaller than fine particles. Remember that nano, in terms of values, is 1 times 10 to the power of minus 9 meters. So very, very, very small. So why would we want to use these particles which are very, very small instead of these larger ones? Well, what do we want to do? We want to take away the dirt from these windows. So what we're doing is we're trying to have a contact between the dirt particles and our nanoparticles. So what's one thing that is good about the nanoparticles? They're smaller. So the nanoparticles being small means that there's a lot of contact between these nanoparticles and the dirt. And that is a property of the nanoparticles, which is a surface area to volume ratio. So the smaller particles, which are the fine ones, the fine particles are going to be a bit larger, so their surface area to volume ratio compared to the nanoparticles are going to be smaller. So our first advantage would be a higher surface area to volume ratio. Now, it says the titanium dioxide helps sunlight break down the dirt particles. Now, what would be the problem if we had these finer particles which were a bit larger? Then they would just get in the way, wouldn't they? Because they'd be occupying the space and then the light would hit them instead of hitting the dirt. So by having the smaller nanoparticles now, it means that more light is able to pass through and break down the dirt. .2 Titanium is extracted from titanium dioxide in a 2-stage process. The equation for the first stage in the process is shown. Calculate the volume of chlorine gas needed to react completely with 100 kilograms of titanium dioxide. The relative atomic masses of oxygen and titanium are given. The volume of 1 mole of a gas is 24 decimeter cubed. 6 marks. Right, so from the information in this question, the way that this is phrased here, we are dealing with reacting masses. So we have to use our reacting masses knowledge to answer this question. Why is this question a bit more tricky though? Is because they want us to use volume also as well as mass. Now, by them giving us the volume of 1 mole of a gas, it's hinting to us to remind ourselves of our equation that's to do with gas volume. So that would be number of moles will be equal to the volume of that gas multiplied by that standard, which is 24. So what do we need to do with reacting masses now? Well, the first thing that we need to do, you can put it on the side here, are our steps. So we need to find out what masses we have, and then using the masses and any relative atomic masses we are given, we can find the number of moles, and then from there a molar ratio, and then ultimately we'll be able to fill out the missing mass that we'd have. But of course in this problem now we have to find volume instead, so our last thing that we could put would be the volume. Now we're comparing that to this equation here. Remember that we want to find out the volume of chlorine gas, and we want to react that with the titanium dioxide. So these are the two substances that we are actually focusing on. So let's start with the masses. In the question they've given us 100 kilograms of titanium dioxide. However, we are dealing with masses, so that means that our standard unit when we're dealing with masses here in this case would be grams, because we are comparing it to our relative atomic mass, which is also going to be in grams. So we need to convert this 100 kilograms to grams. So conversion of kilograms to grams is multiplying by 1000. So 100 multiplied by 1000 is 100,000 grams. So we have 100,000 grams of this titanium dioxide. Chlorine gas, we don't know the mass of it. So to find the number of moles now, we need the relative formula mass of titanium dioxide. So to find the relative formula mass of titanium dioxide, it will be 48 plus 16 times 2, because you have 2 oxygen atoms there. So that would be 48 plus 32, which is 80. So our RFM of titanium dioxide is 80. We want to then find the number of moles. So to find number of moles, that will be the mass divided by RFM. So in this case now, that's 100,000 divided by 80. And then a calculator, we get 1,250 moles of titanium dioxide. Now, we don't know the number of moles of chlorine, but we can find that out by using our equation. So going back to our equation now, trying to find out the molar ratio. So we're looking for the numbers in front of our substances that we're interested in. So if we look at titanium dioxide, there's no number, so that means that it's a 1. And for chlorine, there is a 2. So that means for every 1 mole of titanium dioxide, we have 2 moles of chlorine. So if we have 1,250 moles of titanium dioxide, you just need to double that to find the number of moles of chlorine. So 1,250 multiplied by 2 is 2,500. So we actually have 2,500 moles of chlorine. So we've got the number of moles now of chlorine. So to find our volume now, we can just plug it into our equation here. So we're trying to find the volume. We know that our moles is 2,500 now. We need to just multiply that by 24, and that will give us a value of 60,000 decimeter cubed. So our final volume 60,000 decimeter cubed.